Hello all and welcome to this video where we are going to look at the connection between binomial distributions, which we have done previously, and the normal distributions, which we have been doing recently. What I'm going to start with is just going into the statistics window in the calculator. We're going to do a distribution calculation. Now if we go up from normal, where is it? No, not normal. Binomial, we're going down. We want to do a binomial just to start with. You don't have to be doing this, but just following along. And let's do, we still have to put an X, the number of trials we want to make, but let's go 5, and number of trials that we want to actually run. Let's just start with 5, and actually we'll set that to 1, just success 1. And the probability of success, let's just go 0.2. We'll start with something low. Hit next. It's done the calculating. So the probability of getting one trial correct when we're doing 5 trials, with the probability of any one trial being right, is 0.409. If we graph that, we can actually see the binomial breakdown. So each column is representing, because it is a binomial. I should be able to. I can't click across on. Oh, there we go. Now I can finally click across. Okay, so we can see in the bottom of the graph XC0. So what's the probability of 0 trials being successful? That's 0.32. Probability of 1 trial is 0.40. Probability of being successful on 2 out of the 5 is 0.2. Blah blah blah, and it clearly dips away to that. The probability of being having success on all 5, when the probability of only one of them is 0.2, that's a pretty darn low. And what we're going to play with, I just have to hit back a couple times. We're going to just keep boosting the number of trials. We're going to go to 10, next, recalculate, regraph. We can see the graph changes, okay? And we're going to get some bit more data. And we're going to do this again. We're going to go to 15 trials, regraph. Okay. You might notice something's happening to this shape. If we go back quickly to 5, you'll notice we were very skewed to the left-hand side, which made sense. Because of the low probability, it's more likely we're going to have only 1 or very minimal trials to succeed, and very likely to have not a whole lot. But when we start adding number of trials, and let's go up to 20. Oh, I need to hit back. Let's go up to 20 now. Okay, graph that. You can see actually the most likely outcome, because we're running 20 trials, the most likely outcome is actually have success on 4 of them. Because when you've got 0.2 as the probability of 1 success, if you're running 20 times, you're actually going to have success probably a couple times. In this case, it's 4 times. And maybe, if you think back to the topic we've currently been doing, you'll notice that there is this shape connection that we've been looking at recently. So if I now go back, let's bump this all the way up to 30. We'll go 30. Graph that. Like, oh geez, that's looking pretty similar. It's still skewed to the left. Like if we look at the whole x-axis, this graph is happening all down, almost below 10, like where's 10, 13. Okay, we're doing 30 trials, and pretty much after 13, it's effectively 0. Like that's 9.2 times 10 to the negative 3. That's pretty darn low. But the shape itself for that area where the likely outcomes are to be is looking very much like a normal distribution. If I actually bump, let's go 50 quickly, just to show you this pattern. Okay. Still skewed to the left, and the left bar to the middle is still just a little bit bigger. But if I go back and now I go 100, next, graph that, that's a mighty normal distribution looking. Okay. And this happens as we increase the number of trials. As we start to get more and more trials, the binomial distribution is always going to trend towards, that spread is going to trend towards a normal distribution shape. And if you follow the chain of thoughts of there's going to be a most likely outcome, and then as we spread from that, it's less and less likely to get less successes or more successes from that point. We just need to have enough trials for this pattern to emerge. This also happens if we start to increase the probability, if we go 0.5, this is gonna, I need to, X max, let's go 50. Ooh, zoom. Where's it? No, not that one. Where are we gonna, let's go. How many trials? Oh, we're doing 100 trials, I think. Oh, I mean, Y max. I need to set that to, let's just go 5 for now. That's too far. But you get the idea. If I zoom in, and I'm wasting a bit of time here, let's go to, okay, we can see that there is that normal distribution there. There we go, that's better. Okay, and I don't know why I set the Y scale greater than 1, because we can't have probabilities greater than 1, but we can see that's pretty much perfect for a normal distribution. And we're going to use this, and that's what we're going to look at now, is, let me close that window. Okay, we're going to look at, we can, I'm going the wrong way, here we go. Okay, when n and p, especially when n gets large enough, and that's what these tables are showing, if you pause you can look that the n values are going up in each case. As the n value gets larger, the binomial distribution gets more and more like a normal distribution, the spread. So when n is large enough, and when p, and this is a key thing though, if p is really close to 0 or really close to 1, then it makes it a lot harder. But if we're somewhere sort of near the middle, and you can see even here 0.2, 0.8, it's pretty close to normal when we've got 100 trials. We can, instead of working binomially, we can work as a normal distribution. Now the rule we're going to use is, when are we close enough? When is n and p lined up enough that we can say it's going to work as a normal distribution? We're going to use the textbook trend at the moment. We're going to say where n times p, and then also n times 1 minus p must both be greater than 5. Okay? So in both of these cases, as n gets bigger, well, we're going to get closer to 5. If p is too close to 1, well, n times p is going to be good, but then n times 1 minus p is no good. So that's what gets rid of those bands. As p is closer to the middle, either of those two values are both going to be greater than 5. And we need both of them to be greater than 5. It's no good only one of them. Because if only one of them is greater than 5, it means your data is really skewed. And from that, what we can take away is, if n is sufficiently large and p is an okay value, and we meet this requirement, what we get to do is say that, where have I put my pen down? We get to say that the mean, now, we get to use some normal distribution work, even though it's a binomial, we get to say the mean is equal to np, and the standard deviation is going to be the square root of np 1 minus p. And we're going to use those. Okay, so a quick example. Sample of 1,000 people from a certain city were asked to indicate whether or not they were in favour of construction. So we've got a fixed amount of trials. We are either in favour or not in favour. So this is it's a yes/no, okay, or only two options. 30% of the people are in favour of the new freeway. So the probability, the probability of someone liking the freeway is 0.3. and n is 1,000, and this is a binomial situation. Find the approximate probability that between 270 and 330 people in the sample are going to be in favour of the new freeway. So as I said, n is 1,000, p is 0.03. Now let's check if this situation we can use a continuous distribution to estimate it. N times p is 300, so tick, that's greater than 5, and n times by 1 minus p is 700. So tick, that is also fine. So we can estimate this as a normal distribution instead of dealing binomially. And we want to calculate our mean standard deviation. So our mean is 300, which follows on, makes sense from 0.3, and our standard deviation is going to be the square root of 210, and we'll just leave it as that for now. Just following those two equations on from the last line. Only use these equations if we get success for these requirements. Now from there, if we go back to our calc, if we go main, okay, we can now do an interactive, okay, and we're going to do a distribution. We're going to do continuous, normal, and we want to do a CDF because we want to do a range. Okay. And our lower bound we have is 270, and it's not clicking. Why are you not going in? 270. Our upper bound, we want to know what was between 330. Okay. Our mean that we calculated from the previous slide was 300. Our mean was 300, and our standard deviation was the square root of 210, and we can even put that in. Run OK, and straight away there we... Where did it go? Oh, let's put it on that line there. Oh, it's gone into a weird line, my apologies. Let's drag that down there. Run enter and we get 0.9615. So the likelihood when we run our survey of 1,000 people, the likelihood of getting between 270 and 330 people that say that they are in favour of the freeway is 0.96. Which we got over here. Okay, we could also do a binomial CDF, get roughly the same answer. We could also, because we know our mean, we know our standard deviation from the previous slide, we could also convert these to z-scores, to get a z-score of that, and work using a standardized normal distribution as well, which is sort of the reason why you'd want to estimate a binomial, is as we've looked at in 16D when we've got those sort of problems where you don't know the mean and standard deviation. Working in z-scores, going to a normal, it almost allows us to work backwards to a binomial. So let's do one more quick example and we'll leave it there. So a sample of 60 Year 12 students from Lara Secondary College were asked if they were going to attend the Year 12 formal. It is known 65% of the students in Year 12 will be attending. Find the approximate probability that 36 and 48% of the students from the sample were going to attend the form. And let's say that it's 65% of the Year 12s will be attending, is that it's probably better to say that they want to attend. That's probably a better scenario, because if it was 65% going, you just find 65% of 60 and say that's what it is. But we know 65% want to. So in this case, n is 60 because there's 60 students. The probability of them going is 0, or because they want to go, is 0.65 for each individual student. And we want to check if we can estimate, model this with a normal distribution instead. So NP is 60 times by 0.65, which 60 times 0.65 is 39. So we meet that requirement, tick, and then we're going to do n by 1 minus p. Let me make sure I've got that right. The check, yes, n by 1 minus p. Okay, we've got 60 times by, that's going to be 0.35. 60 by 0.35. That gives us 21, so also greater than 5. So yes, we can use this to estimate. So mean is going to be NP, which we already found, which is 39, and our standard deviation from the equation back here is square root of NP1 minus P is equal to the square root of NP1 minus P. So that is going to be, we know NP is 39, so I'm just going to put that in there. 1 minus P is 0.35. So we get 39 by 0.35, just simplifying on the fly. That is going to be 39 by 0.35. Okay, that's not nice looking, but we can still put it in to the calculator. So it's the square root of 130.65 all divided by 10. So we've got our mean standard deviation. Now we just want to find the probability that x is going to be between 36 and 48. Okay. And we can do that on our CAS, just doing a normal distribution. Continuous, normal. Okay, our lower bound is 36. Our upper bound is 48. Our standard deviation is square root 1365 divided by 10, and our mean was 39. Go OK, and that is going to be equal to 0.7842 to 4 decimal places. And that's it. We could have done it with a binomial, but like I said, we'll spend a little bit more time looking at when we use z-scores in class to help do problems of that nature. As always, if you have any questions, put them below or ask in class. Otherwise, have a good day.